Welcome everyone. I'm excited to kick off this presentation on the lubrication system. Today, we'll explore the essentials of how lubrication keeps machinery running smoothly. We'll cover the key components, types, and maintenance tips. Let's get started and dive into the world of lubrication systems. Let's talk about the purpose of a lubrication system. The primary goal here is to supply oil to various parts of the engine. Think of it as the engine's lifeline, ensuring everything runs smoothly. This oil doesn't just lubricate, it also plays a crucial role in cooling the engine components, helping to keep temperatures in check. Additionally, it works to clean away dirt and debris that can cause wear and tear. By reducing friction, the lubrication system helps prevent parts from grinding against each other, which extends the engine's life and improves performance. So, in essence, this system is vital for maintaining the health and efficiency of the engine, tying into our overall theme of engine reliability and longevity. The purpose of the oil system in turbine engines is primarily to cool the bearings. It does this by carrying heat away from the bearings through circulating oil around them. This process is essential to keep the bearings at optimal temperatures and prevent overheating. In some engines, we also see air cooling used alongside oil cooling to enhance the cooling effectiveness. This combination helps ensure the bearings stay cool under various operating conditions. Overall, the oil system plays a crucial role in maintaining the reliability and efficiency of the engine by effectively managing heat. Today, we're going to look at the two basic classifications of lubrication systems that are commonly used in engines. The first one is the wet sump system. In this setup, the oil is stored in a sump at the bottom of the engine, and the oil pump circulates it throughout the engine components. It's simple, reliable, and widely used in many applications. The second classification is the dry sump system. Here, instead of storing oil in the engine itself, the oil is stored in a separate tank. The oil pump then draws oil from this tank and circulates it through the engine. This setup offers advantages like better oil control, reduced engine height, and improved cooling, especially useful in high-performance or racing engines. Both of these systems serve the same fundamental purpose: to lubricate, cool, and protect engine components, but they are suited to different types of engines and operational demands. Understanding these classifications helps us see how the design choices impact engine performance and reliability, which is a key theme in our overall discussion of engine systems. Today, we're going to look at the wet sump system. A wet sump system is a type of lubrication system where the oil supply is stored within the engine itself, typically in a sump or pan located at the bottom of the engine. This oil is carried within the engine or sometimes within the accessory gearbox. The key point here is that the oil is stored directly in the engine, which makes this system simple and compact. It's a common setup in many engines because it's reliable and cost-effective. The oil in the sump circulates through the engine to lubricate moving parts, then returns back to the sump for recirculation. This cycle is crucial for engine health and performance. Connecting this to the overall theme, understanding the wet sump system helps us appreciate how lubrication is managed efficiently in many engines, ensuring smooth operation and longevity. This system's simplicity is part of what makes it so widely used in various applications. Now, let's take a closer look at the wet sump oil system. This is one of the most common types of oil lubrication systems used in engines. Essentially, in a wet sump setup, the oil is stored in a sump located at the bottom of the engine. From there, the oil is picked up by the oil pump, which is responsible for circulating it throughout the engine. The oil then passes through a filter, which is crucial because it removes any dirt or debris that could cause damage or reduce efficiency. The key components here are the sump, the filter, and the pump, all working together to ensure that the engine stays properly lubricated. This system is simple, reliable, and cost-effective, which is why it's widely used in many engines. Remember, maintaining a clean oil filter and adequate oil levels in the sump is vital for engine health and performance. Now, let's take a look at the dry sump lubrication system. This type of system carries its oil supply in a dedicated tank, separate from the engine itself. It's actually the most common type of lubrication system used in modern gas turbine engines. The main advantage here is that by having the oil in a separate tank, we can better control the oil flow and ensure proper lubrication even under varying operating conditions. This setup helps maintain a steady supply of clean oil, which is crucial for the engine's performance and longevity. As we continue exploring different lubrication systems, keep in mind that the dry sump design is favored for its efficiency and reliability in high-demand environments. Let's take a closer look at the dry sump oil system. On this slide, you can see the main components involved. First, we have the filter, which is essential for removing contaminants from the oil to keep the system clean and functioning smoothly. Next is the pump, responsible for circulating the oil throughout the engine and the system. Then, there's the tank, which stores the oil and helps maintain proper oil levels and temperature. The scavenger pump plays a crucial role as well, as it helps remove excess oil from the crankcase and send it back to the tank. This setup is especially important in high-performance engines because it offers better oil control, reduces the risk of oil starvation, and allows for a more compact engine design. Overall, the dry sump system ensures reliable lubrication and cooling, which are vital for the engine's performance and longevity. Remember, each component works together seamlessly to maintain optimal oil flow and system health. Let's take a closer look at the key components involved in an oil lubrication system. First up, we have the oil tank, which serves as the reservoir for storing the oil. The oil pump then draws oil from this tank and circulates it through the system. To ensure the oil remains clean and free of debris, there's an oil filter that traps impurities. Next, we have the oil pressure regulating valve, which helps maintain a consistent pressure within the system, preventing damage or leaks. Alongside that, the oil pressure relief valve acts as a safety mechanism, releasing excess pressure to protect the components. The pressure regulating valve, similarly, ensures that the oil pressure stays within optimal ranges for efficient lubrication. Moving on, oil jets play a critical role in delivering a focused stream of oil directly to specific engine parts that require precise cooling and lubrication. Altogether, these components work in harmony to guarantee that the engine receives the right amount of oil at the right pressure, which is essential for smooth operation and longevity. This interconnected setup highlights how vital proper lubrication management is to the overall health of an engine. Let's take a moment to look at this image of an oil tank. Now, these tanks are a crucial part of the energy infrastructure, serving as storage for oil before it's transported or refined. What's important to understand is that these tanks help manage supply and demand, ensuring that oil is available when needed. They can vary significantly in size and design, depending on the specific needs of the facility or the region. This image highlights the scale and complexity involved in handling such a vital resource. Proper storage is key to maintaining safety, preventing leaks, and minimizing environmental impact. Throughout this presentation, we see how these elements fit into the larger picture of energy production and management. So, when we think about oil tanks, we're really looking at a critical link in the entire energy supply chain, supporting economic activity and energy security. Today, I want to talk about the oil tank and its crucial role in aircraft engine operation. The main purpose of the oil tank is to store oil, which is essential for keeping the engine running smoothly. It acts as a reservoir, ensuring that there's always an adequate supply of oil available. One of the key features of this design is that it provides a constant supply of oil to the engine, no matter what attitude the aircraft is flying in. Whether the aircraft is climbing, descending, or turning, the oil flow remains steady. This consistency is vital because it helps prevent engine wear and overheating. So, in essence, the oil tank isn't just about storage. It's about maintaining reliable engine performance under all flight conditions. Let's take a closer look at the construction of the oil tank. One key aspect is the welded construction with internal stiffeners. This approach ensures the tank is both strong and durable, effectively handling the stresses it encounters during operation. The welds provide a seamless, robust connection that minimizes the risk of leaks or failure. Another important feature is the filler neck. This component is designed for safe and efficient filling of the tank, making sure the process is smooth and secure. Its placement and design are crucial to prevent spillage and to maintain the integrity of the tank. Overall, these construction details, welded with internal stiffeners and the well-designed filler neck, are vital for ensuring the oil tank operates reliably and safely. They are fundamental to the overall integrity and performance of the system we're discussing today. Let's take a closer look at some key components related to oil tank construction. First, we have the dipstick. This is an essential tool for checking the oil level inside the tank. It helps ensure that the oil quantity remains within the proper range for safe and efficient operation. Next, we have the relief valve, which is critical for safety. It limits the air pressure inside the tank, preventing overpressurization that could lead to damage or failure. Understanding how these parts work together is vital for maintaining the integrity and safety of the oil tank. And speaking of construction, we'll also explore how oil tanks are built, including the materials and design considerations involved. All these points tie into the overall theme of ensuring safe and reliable operation of the equipment. Let's take a closer look at the gauze filter and oil tank construction. The gauze filter plays a crucial role in our system by capturing impurities and preventing contaminants from entering sensitive components. Its design ensures that only clean, filtered oil circulates, which is vital for maintaining overall efficiency and longevity. When it comes to oil tank construction, durability and proper sealing are key. A well-constructed tank not only holds the oil securely, but also minimizes leaks and contamination. Understanding these elements helps us appreciate how each part contributes to the reliability and performance of the entire system. These points tie back to our broader theme of ensuring optimal operation through thoughtful design and quality materials. Let's take a closer look at the oil tank construction, starting with the oil quantity transmitter. This component is crucial because it helps us accurately measure the amount of oil in the tank, ensuring we maintain the right levels for efficient operation. It provides real-time data, which is vital for monitoring and controlling the system effectively. Next, we have the drain cock. This might seem like a small part, but it's very important for maintenance. The drain cock allows us to safely and easily remove any accumulated water or sludge from the bottom of the tank. Regular draining helps prevent corrosion and keeps the oil clean, which ultimately extends the life of the equipment. Overall, these components, the oil quantity transmitter and drain cock, are integral to the proper construction and maintenance of the oil tank. They work together to ensure the system runs smoothly, reliably, and safely, which ties back to our goal of efficient and sustainable operation throughout the entire process. Pressure buildup is actually a key aspect of maintaining proper oil flow within the system. By creating a certain amount of pressure inside the tank, we ensure that oil is pushed consistently and reliably towards the oil pump inlet. This positive pressure helps prevent issues like air pockets or inconsistent flow, which can affect overall performance. When the pressure is maintained correctly, it guarantees a steady supply of oil, supporting the efficient operation of the entire lubrication system. This is crucial because, as we've discussed earlier, a reliable oil supply is fundamental to the health and longevity of the machinery. So, in essence, managing pressure within the oil tank isn't just about keeping things sealed. It's about ensuring the oil flow remains positive and continuous, which is essential for optimal system performance. This pressure buildup is made possible by running the vent line through an adjustable check relief valve. What this means is that we can control the pressure in the system more precisely. The check relief valve allows gases or vapors to escape when the pressure exceeds a certain limit, preventing overpressurization. The fact that it's adjustable gives us the flexibility to set the right pressure threshold for different operating conditions. Focusing on the oil tank principle, this setup is crucial because it helps maintain safe pressure levels within the tank, avoiding potential leaks or failures. Overall, this is a key safety feature that ensures the system operates smoothly and reliably, which ties into our broader goal of safe and efficient system design. Let's start with the relief valve. It's usually set to relieve at about 4 psi. This is an important safety feature because it helps maintain the right pressure. By doing so, it keeps positive pressure on the oil pump inlet, which is crucial for proper oil flow. If the pressure gets too high, the relief valve opens to prevent damage. Remember, maintaining this pressure ensures the system operates smoothly and safely. Moving on to the oil tank principle, understanding this setup is key because it supports the entire lubrication system. Proper pressure regulation through the relief valve helps us keep the oil flowing efficiently, which is essential for the overall health of the machinery. So, keeping an eye on that relief valve setting is a small step that plays a big role in system reliability. On this slide, we're looking at some tanks that include a deaerator tray. This component plays a crucial role in separating air from the oil that's returned to the tank through the scavenger system. Essentially, as oil circulates back into the tank, any entrapped air is removed by this tray, helping to maintain the oil's quality and prevent issues like cavitation or foam formation. Once the air is separated, it's carried out through a vent system, which ensures the tank remains properly ventilated and prevents pressure buildup. Focusing on the oil tank itself, these tanks are designed to hold and manage the oil efficiently. They're a key part of the overall lubrication system, helping to keep the oil clean, aeration-free, and ready to circulate where it's needed. So, in summary, incorporating a deaerator tray and vent system enhances the tank's ability to keep the oil in optimal condition, which is essential for the smooth operation and longevity of the entire system. The vent system inside the tank is designed in such a way that air is vented at all times. This is a crucial feature because it helps to prevent pressure buildup inside the tank, which could otherwise lead to operational issues or safety hazards. By ensuring continuous venting, the system maintains a balanced pressure environment, allowing the oil to flow smoothly without any disruptions. When we look at the oil tank, the principal focus is on how this vent system contributes to the overall efficiency and safety of the storage process. It's a simple yet vital component that plays a key role in the reliable functioning of the entire system. Let's take a closer look at the oil pump. The oil pump is a crucial component in any engine, as it is responsible for circulating oil throughout the system. Its main job is to ensure that all moving parts are properly lubricated, reducing friction and preventing overheating. Without a functioning oil pump, the engine could quickly overheat or suffer severe wear and tear. The pump operates by creating pressure that pushes the oil through passages in the engine. This pressure is vital because it helps deliver oil to hard-to-reach areas, like the bearings and camshaft. Think of it as the heart of the lubrication system, pumping life into the engine's moving parts. Understanding how the oil pump works ties into the overall theme of engine efficiency and reliability. A well-maintained oil pump ensures smooth performance and longevity of the engine. So, keeping an eye on its condition is essential for optimal operation and preventing costly repairs down the line. Now, let's talk about how oil is supplied under pressure to the different parts of the engine that need lubrication. This is a crucial part of engine maintenance because proper lubrication reduces friction, prevents overheating, and minimizes wear and tear. The oil pump plays a key role here, as it is responsible for circulating the oil through the engine. It's worth noting that oil pumps can come in several different types, each designed to suit specific engine requirements. Despite the variations, their primary function remains the same: to ensure a steady flow of oil under pressure. When we refer to an oil pump, we're talking about the component that constantly pushes the oil to where it's needed most. This process helps keep engine parts running smoothly and efficiently. Understanding how these pumps work and their importance helps us appreciate the complexity behind engine lubrication systems. It's a vital aspect of engine design that ensures longevity and optimal performance over time. When it comes to oil pumps, the most common types you'll encounter are gear and gerotor pumps. These are widely used because of their efficiency and reliability. Among these, gear-type pumps are the most commonly used in various applications. They are favored because they provide a steady flow of oil, which is essential for proper lubrication and cooling in engines and machinery. So, when we talk about oil pumps, understanding these key types helps us appreciate how vital they are in maintaining the health and performance of engines. This slide highlights the two essential elements of a gear-type oil pump, which are crucial for understanding how it functions. The first element is oil delivery, which refers to how the pump moves oil from one part of the system to another, ensuring proper lubrication and cooling. The second element is oil scavenge, or in other words, the process of collecting and returning oil back to the reservoir for recirculation. These two elements are fundamental because they work together to maintain a continuous flow of oil, keeping the system well lubricated and preventing overheating. When we think about the overall oil pump operation, it's the balance between delivery and scavenge that keeps everything running smoothly. So, in essence, a gear-type oil pump relies on these two key functions, delivering oil where it's needed and scavenging it back, making it a vital component in many lubrication systems. Understanding these elements helps us appreciate how efficient and reliable these pumps are in maintaining the health of the machinery. Some types of pumps, including the gear-type oil pump, may have several elements working together. This design allows for efficient movement of oil within machinery. The gear-type oil pump specifically uses intermeshing gears to transfer oil from the inlet to the outlet. This mechanism is simple yet effective, making it a popular choice for various applications. It's important to understand that the gear elements are crucial because they determine the flow rate and pressure of the oil being pumped. Recognizing the role of these elements helps us appreciate how different pump types are optimized for specific needs. Overall, understanding these elements helps us select the right pump for different scenarios in machinery and lubrication systems. Let's talk about the clearances between the gear teeth and the sides of the pump wall and plate. These clearances are absolutely critical because they directly influence the pump's output. If the clearances are too tight, it can cause excessive wear or even damage to the gears and housing. On the other hand, if the clearances are too loose, you risk losing efficiency and potentially affecting the pump's ability to generate the correct flow rate. It's particularly important in gear-type oil pumps, where precise clearances ensure that the pump maintains the right pressure and volume. Proper clearances help in achieving optimal performance, preventing leaks, and extending the lifespan of the pump. So, when designing or maintaining these pumps, always pay close attention to these gaps. They are key to ensuring the pump functions reliably and efficiently over time. This focus on clearances ties back to our overall goal of achieving a well-maintained, high-performing hydraulic system. The number of pumping elements that are used to pump oil pressure and scavenge really depends on the specific type and model of the engine we're working with. Different engines have different requirements, so their oil pumping systems are designed accordingly. When we look at gear-type oil pumps, for example, they are typically straightforward but highly effective. These pumps often use gears to move oil efficiently through the system. The key point here is that the pump's design and the number of elements directly impact how well the engine is lubricated and how reliably it operates under various conditions. So, understanding these differences helps us appreciate the importance of matching the pump type and configuration to the engine's needs, ensuring optimal performance and longevity. Let's take a closer look at how we can accommodate larger capacities of oil and air in our systems. One effective way is by utilizing various scavenging oil pump elements. These components are designed to handle increased flow requirements, ensuring the system runs smoothly even under higher loads. Specifically, when we talk about gear-type oil pumps, they are a popular choice due to their efficiency and reliability. Gear pumps work by trapping oil between two gears and moving it through the pump, which makes them excellent for maintaining a steady flow of oil. By incorporating these gear-type pumps, we can effectively manage larger volumes of oil and air, which is essential for optimizing overall system performance. This approach aligns well with our goal of enhancing capacity and ensuring durability in our machinery. So, in summary, selecting the right scavenging pump elements, like gear-type oil pumps, is crucial for supporting higher capacities and maintaining efficient operation in demanding conditions. Now, let's look at how scavenging elements function within the lubrication system. These elements are designed with a greater pumping capacity compared to the pressure elements. Why is that important? Well, their primary role is to ensure that any excess oil doesn't stay in the bearing sumps of the engine. By having a higher capacity, they effectively remove oil that might otherwise accumulate and cause issues. In particular, when we focus on gear-type oil pumps, they are commonly used for this purpose. Their robust design allows them to quickly and efficiently scavenge oil from critical areas, maintaining the proper oil level and preventing oil buildup. This is a crucial aspect of engine lubrication because it helps maintain optimal operating conditions and prevents potential damage caused by oil pooling or inadequate removal. So, in essence, the scavenging system acts as a safeguard, ensuring the engine stays clean and well lubricated, which ties back into the overall theme of effective engine maintenance and performance. On this slide, we're looking at how the gerotor pump manages oil flow within the system. Usually, there is a single element dedicated to controlling oil pressure, which is crucial for maintaining proper system function. In addition, there are several elements responsible for scavenging oil, and these are designed quite similarly to the pressure element. The shape of these scavenging elements is almost identical, which helps streamline manufacturing and maintenance. One of the key points here is that the capacity of these elements can be adjusted by changing the size of the gerotor elements themselves. This flexibility allows us to fine-tune the pump's performance to meet specific system requirements. Remember, the overall goal of using a gerotor pump is to efficiently circulate oil, ensuring proper lubrication and pressure throughout the system. By understanding how these elements work together and how their sizes can be varied, we can optimize the pump's performance for different applications. Each set of gerotor is separated by a steel plate, which is a crucial detail in the construction. This separation essentially makes each set an individual pumping unit. Now, these units are composed of two main components, an inner element and an outer element. The inner element typically has teeth that engage with the outer element, which also has teeth, but arranged in a way that allows for the pumping action. Understanding this structure helps us see how the gerotor pump functions efficiently. The steel plates not only provide separation, but also help maintain the alignment and integrity of each pumping unit. This modular setup is part of what makes gerotor pumps reliable and versatile in various applications. Overall, this layered construction with distinct inner and outer elements highlights the precision engineering behind the gerotor design. Let's take a closer look at the construction of the gerotor pump, starting with this small, star-shaped inner element. As you can see, it features external lobes that are carefully designed to fit within the internal lobes of the surrounding structure. This precise matching is crucial because it ensures an effective seal and smooth operation. The way these lobes interlock allows the rotor to rotate efficiently, minimizing leakage and maximizing performance. Understanding this intricate design helps us appreciate how the gerotor pump achieves its reliability and efficiency, key factors in its overall function within fluid systems. Now let's take a closer look at the construction of the gerotor pump. The small element you'll notice fits directly onto the pump shaft and is keyed to it. This means it's securely attached and acts as the drive for the turning element. Essentially, it transmits the rotational force from the shaft to the other parts of the pump. Then we have the outer element, which fits within a steel plate. This steel plate isn't just a simple holder. It actually has an eccentric bore, meaning it's slightly off-center. This eccentricity is crucial because it allows for the movement and operation of the pump's internal components in a precise manner. Together, these parts form the core of the gerotor pump's construction, enabling efficient and reliable operation by ensuring the drive is securely connected and properly aligned within the pump housing. This design highlights the importance of carefully engineered components working together to achieve optimal performance. In one engine model, the oil pump is actually made up of 4 key elements. The first one is dedicated to oil feed, which is responsible for supplying fresh oil to various engine parts that need lubrication. This ensures that everything runs smoothly and components are protected from wear and tear. Then, we have three elements focused on scavenge. These work together to remove the oil after it has done its job of lubricating the engine parts. The scavenging process is crucial because it helps maintain the proper oil level and prevents excess oil from accumulating in the engine, which could cause issues like increased pressure or overheating. Understanding these four components is vital because it highlights how the oil pump not only delivers oil where it's needed, but also efficiently removes it to keep the engine clean and well lubricated. This balance between feed and scavenge is a fundamental part of engine design that ensures optimal performance and longevity. In some other models, the pumps actually have 6 elements. One of these elements is dedicated to feed, which is responsible for supplying the fluid into the system. The remaining 5 elements are used for scavenge, which essentially means they help recover and remove the fluid or vapors that need to be separated or vented out. This configuration highlights how different pump designs can be tailored to specific operational needs, especially in complex systems where managing both intake and exhaust efficiently is crucial. Understanding these variations helps us appreciate the flexibility and adaptability of pump designs within the broader context of system performance and reliability. Let's take a closer look at the regulating valve. This component plays a crucial role in controlling the flow and pressure within a system. Essentially, it adjusts the flow rate to maintain desired operating conditions, making sure everything runs smoothly. The key point here is that it's not just about opening or closing a valve, but precisely modulating flow to match system demands. This is especially important for maintaining safety, efficiency, and stability in industrial processes. As we connect this to the overall theme, remember that the regulating valve is a vital control element that helps us optimize system performance and prevent issues caused by pressure fluctuations. Understanding how it functions gives us better insight into the complexity and precision involved in process control systems. The regulating valve is located on the discharge side of the pump, which is a key point to remember. Its main purpose is to control the flow and pressure of the fluid as it exits the pump. By adjusting this valve, we can maintain the desired system pressure and prevent any potential damage caused by excess pressure. This component plays a crucial role in ensuring the pump operates efficiently and safely, especially under varying load conditions. Connecting this to the overall system, the regulating valve helps us fine-tune the process, ensuring smooth operation and protecting other equipment downstream. So, always keep in mind that the discharge side is where we manage flow control, making the regulating valve a vital part of the pump system. Let's take a closer look at how we control the pump's output pressure. This slide highlights the role of a regulating valve. Essentially, the valve limits the pressure by bypassing oil back to the pump's inlet whenever the outlet pressure exceeds a certain preset limit. This prevents the system from experiencing excessive pressure, which could cause damage or inefficiency. The key point here is that the regulating valve acts as a safeguard, maintaining a consistent and safe pressure level. This is important within the overall system because it ensures reliable operation and protects other components from stress due to high pressure. By effectively managing pressure in this way, we help improve the longevity and performance of the entire hydraulic system. Now, this slide highlights some important safety and operational features. First, it can be adjusted if required to bring the oil pressure within limits. This means that if the oil pressure gets too high or too low, we have the flexibility to make adjustments to maintain optimal levels. Maintaining proper oil pressure is crucial for the system's health and efficiency. Next, we see that the shaft shear section causes the shaft to shear if the pump gears seize up. Essentially, this is a protective mechanism. If the gears stop moving due to some blockage or failure, this shear section will break away to prevent more serious damage to the shaft or the entire system. Finally, we have the regulating valve. This component plays a vital role in controlling the flow and pressure within the system, ensuring everything runs smoothly and safely. When we look at these features together, it's clear how they work in concert to protect the equipment and keep the operation within safe and efficient parameters. Let's talk about the oil filter. This component might seem small, but it plays a crucial role in maintaining your engine's health. Its main job is to trap dirt, debris, and contaminants that can accumulate in the oil over time. By filtering out these particles, the oil stays clean and effective at lubricating engine parts. A clean oil filter helps ensure that your engine runs smoothly and reduces wear and tear. It's important to change the oil filter regularly, usually at each oil change, to keep the filtration system working efficiently. Neglecting this can lead to contaminated oil circulating through your engine, which can cause damage over time. So, in the context of overall engine maintenance, the oil filter is a key component that supports optimal engine performance and longevity. Keeping it in good condition is just as important as changing the oil itself. Now, let's talk about the role of oil filters. Their main job is to remove foreign particles that may be present in the oil. These tiny contaminants can come from various sources, like manufacturing debris or wear particles from engine components. This cleaning process is especially crucial in gas turbines, where even small particles can cause significant damage or reduce efficiency. By filtering out these impurities, we help protect the vital parts of the turbine and ensure smooth operation. So, the oil filter acts as a critical barrier, maintaining the cleanliness of the oil. This not only prolongs the life of the equipment, but also helps maintain optimal performance. Remember, clean oil is essential for the overall health and efficiency of any lubrication system, especially in demanding environments like gas turbines. As high engine speeds are reached, it's really important to understand how anti-friction ball and roller bearings behave under these conditions. When the engine is operating at these elevated speeds, any contamination in the oil can cause serious damage to these bearings. That's because contaminated oil can increase friction and wear, leading to rapid deterioration. This is where the oil filter becomes crucial. It plays a vital role in removing impurities from the oil, ensuring that only clean oil circulates through the bearings and other engine components. Maintaining clean oil helps prolong the life of the bearings and keeps the engine running smoothly at high speeds. So, in essence, the oil filter is a key component in protecting the engine's moving parts, especially when operating under demanding conditions like high speeds. There are usually numerous drilled or core passages that lead to various points of lubrication within the system. These passages are typically quite small, which is important to note because their size makes them prone to clogging. When these passages become blocked, it can significantly affect the flow of oil and, ultimately, the performance of the machinery. That's why an oil filter is so critical. It acts as a safeguard, trapping debris and contaminants before they reach these narrow passages. Keeping these passages clear ensures smooth lubrication and helps prevent potential damage or failure. Throughout the overall system, maintaining clean passages and an effective oil filter system is essential for reliable operation and longevity. Now, let's take a look at the various types and locations of filters used for filtering turbine lubricating oil. As you can see, oil filters play a crucial role in maintaining the cleanliness of the oil, which is essential for the smooth operation and longevity of the turbine. Different types of filters are employed depending on the specific requirements, such as the level of filtration needed and the location within the system. These filters are strategically placed at various points in the lubrication system to ensure contaminants are effectively removed before the oil circulates through critical components. The key is to understand that proper filtration not only protects the turbine components, but also helps prevent unexpected downtime and costly repairs. So, selecting the right type of filter and placing it correctly within the system are vital steps in ensuring optimal performance and durability of the turbine. Filtering elements come in a variety of configurations and mesh sizes, which is an important point to understand when selecting the right filter for a specific application. The configurations can differ based on the design and purpose, allowing for different flow rates or filtration efficiencies. When we talk about mesh sizes, these are measured in microns, and that measurement tells us the size of the particles the filter can trap. A smaller micron rating means the filter can capture finer particles, which is crucial for protecting sensitive components or ensuring cleaner fluids. For example, an oil filter with a fine mesh will remove more contaminants, helping to extend the life of engines and machinery. So, understanding these variations helps us choose the most effective filter for each situation, reinforcing the overall importance of proper filtration in maintaining system performance and longevity. A linear measurement equal to 1/1,000,000th of a meter, which is incredibly tiny, is often used to describe very small openings or features. This tiny measurement helps us understand just how precise and detailed our engineering and manufacturing processes need to be. For example, when we talk about an oil filter, we're dealing with very small particles that need to be removed to keep engines running smoothly. The filter's effectiveness depends on its ability to trap these microscopic contaminants. So, understanding these minuscule measurements is crucial because it highlights the level of precision required in designing and manufacturing components like oil filters. It all ties back to the importance of accuracy and attention to detail in maintaining the performance and longevity of mechanical systems. Now, let's take a closer look at the filtering element interior. It's made of various materials, which is quite interesting. These materials include paper and metal mesh. The choice of materials is crucial because it affects how effectively the filter performs. For example, paper filters are great at trapping smaller particles, while metal mesh can provide durability and support. When we talk about oil filters, this interior component plays a vital role in keeping the engine oil clean. A well-designed filter ensures that contaminants don't circulate through the engine, which helps maintain engine health and efficiency. So, understanding the materials used in these filtering elements helps us appreciate the complexity and importance of the oil filter in the overall lubrication system. Oil normally flows through the filter element from the outside into the filter body. This is a key point because it highlights how the filtration process works in most oil filters. The oil enters the filter from the outside, passing through the filter media, which traps dirt and debris. Once filtered, the clean oil then flows inward and continues through the engine system. Understanding this flow direction is important because it affects how we maintain and replace filters to ensure optimal engine performance. By designing filters to work this way, manufacturers help ensure that contaminants are effectively removed before the oil circulates back into the engine, keeping everything running smoothly. Now, let's take a closer look at the different types of oil filters. One common type uses a replaceable laminated paper element. These are popular because they are cost-effective and easy to replace during regular maintenance. The laminated paper is designed to trap dirt and debris effectively while allowing oil to flow freely. Another type of oil filter employs a very fine stainless steel metal mesh, typically around 25 to 35 microns in pore size. This mesh acts as a filter medium that can be cleaned and reused, offering a different approach to filtration. The fine mesh ensures that even tiny particles are captured, helping to protect the engine components more thoroughly. Both types of filters are essential for maintaining engine health, but they serve slightly different purposes depending on the application and maintenance preferences. The key takeaway is that choosing the right filter involves understanding these materials and their filtration capabilities. This connects to our overall theme of ensuring optimal engine performance through proper filtration techniques. Most filters are typically located close to the pressure pump, which makes sense because that's where the oil or hydraulic fluid is under the highest pressure and most susceptible to contaminants. When we look at the components of these filters, you'll notice they usually consist of a filter body or housing, which is the main casing that holds everything together. Inside, there's the filter element itself. This is the part responsible for trapping dirt, debris, and other particles to keep the fluid clean. You'll also find a bypass valve, which plays a crucial role. If the filter gets clogged or becomes too restrictive, the bypass valve allows the fluid to bypass the filter temporarily, ensuring the system keeps circulating without interruption. Along with that, there's a check valve, which prevents backflow and maintains pressure within the system. Specifically, for oil filters, these components work together to protect engine parts from wear and tear caused by contaminants. Remember, The placement and design of these filters are all about ensuring efficient filtration and system reliability. This setup is integral to the overall theme of maintaining system health and preventing damage. Let's talk about the bypass valve in the oil filter. Its main job is to ensure that oil flow isn't completely halted if the filter element gets clogged. This is crucial because it prevents oil from bypassing the filter entirely, which could lead to contaminants circulating through the engine. The bypass valve opens whenever a certain pressure threshold is reached, meaning if the filter becomes too restrictive, the valve will activate. This way, oil can bypass the clogged filter and continue circulating, protecting the engine from oil starvation. Understanding this mechanism highlights how important proper filtration is, but also how the system is designed to maintain continuous oil flow, even under challenging conditions. This balance between filtering and maintaining flow is a key part of the overall oil system's reliability. If this situation occurs, the filtering action is lost, meaning that unfiltered oil can be pumped directly to the bearings. This is a critical point because it can lead to serious damage. When the filter fails or becomes bypassed, the bearings are no longer protected by the filtering process. This situation actually prevents the bearings from receiving no oil at all, which is a good thing in a way, because complete loss of oil would cause immediate and severe damage. However, the problem is that unfiltered oil may contain debris or particles that can cause wear and tear over time. So, the key takeaway here is the importance of the oil filter. It's a vital component that ensures only clean, filtered oil reaches the bearings, protecting the entire system. If the filtering action is compromised, it can lead to longer-term issues, even if immediate failure is avoided. This highlights why maintaining and monitoring the oil filter is so essential for the overall health of the machinery. When an engine is in bypass mode, many models feature a mechanical indicator that actually pops out to signal this condition. This is a handy visual cue because it lets you know immediately if the filter isn't operating as it should. However, it's important to remember that this indicator is only visible when you actually inspect the engine directly. It's not something you can see from a distance or through a dashboard display. Specifically, with the oil filter, this bypass indicator serves as a critical alert. It's designed to warn us that the filter might be bypassing, which could mean there's a blockage or some other issue needing attention. Recognizing this indicator helps us maintain proper engine health and ensures that we're aware of potential problems early on. Overall, this visual cue underscores the importance of routine inspections and being attentive to these mechanical indicators, especially when we're managing engine performance and longevity. In addition to the main oil filters we've discussed earlier, it's important to recognize that there are also secondary filters placed throughout the system. These secondary filters serve various purposes, all aimed at ensuring the oil remains as clean as possible. For example, some of these filters might be located near critical components to provide extra protection, catching smaller particles that the main filter might miss. This layered filtration system is crucial because it helps extend the life of the engine and maintain optimal performance. By having multiple filtering points, we're effectively creating a safety net that keeps contaminants out of sensitive parts. This interconnected approach highlights how comprehensive the oil filtration process really is, and it plays a vital role in the overall health of the engine, which ties back to our theme of maintaining system reliability and efficiency. Let's take a closer look at the final stage in ensuring clean oil for our bearings. Here, we use fine mesh screens known as last chance filters. These filters are positioned just before the oil passes from the spray nozzles onto the bearing surfaces. The main purpose of these filters is to catch any remaining particles or debris that might have bypassed earlier filtration steps. By doing so, they help prevent contaminants from reaching the bearing surfaces, which is crucial for maintaining smooth operation and prolonging the lifespan of the bearings. Think of these last chance filters as the final line of defense, ensuring that only clean, filtered oil makes contact with sensitive components. Incorporating this extra layer of filtration is a key aspect of good maintenance practices and helps us keep the system running efficiently and reliably. These filters are located at each bearing, and help screen out contaminants that could plug the oil spray nozzle. It's really important to understand that these filters play a crucial role in maintaining the health of the entire lubrication system. By catching dirt, debris, or any other unwanted particles, they prevent clogs and ensure that the oil spray remains unobstructed. This way, the oil can reach the bearings effectively, providing proper lubrication and avoiding potential failures. So, always remember that these filters are a small but vital line of defense in keeping the machinery running smoothly and efficiently. Let's take a closer look at the anti-drain check valve. This component plays a crucial role in our system by preventing backflow, which can be quite problematic. Essentially, it ensures that once the fluid flows in one direction, it doesn't reverse and cause issues downstream. This is especially important in maintaining system integrity and preventing contamination or damage. The check valve is designed to open under pressure when fluid moves forward and automatically close when flow stops or reverses. Incorporating an anti-drain feature adds an extra layer of safety, ensuring that residual fluid doesn't drain back and cause potential problems. Overall, this valve is a vital safeguard that helps us maintain reliable and safe operation within the entire system. An anti-drain check valve is incorporated into the assembly to prevent oil in the tank from draining down into the engine sumps when the engine is not operating. This is a crucial feature because it helps maintain proper oil levels and ensures quick, reliable engine startup. The check valve is normally spring-loaded closed, which means it stays shut under normal conditions. It requires about 4 to 6 pounds per square inch of pressure to open, allowing oil to flow when necessary. This design effectively prevents oil from flowing back into the engine when it's not running, contributing to the overall reliability and efficiency of the lubrication system. So, in essence, this anti-drain check valve plays a key role in maintaining proper oil management and protecting the engine's health. All right, let's talk about the pressure regulating valve. This component is essential in maintaining a consistent pressure within a system, ensuring that downstream equipment operates safely and efficiently. Think of it as a guardian that prevents pressure from climbing too high, which could cause damage or safety issues. It works by automatically adjusting itself to release or restrict flow as needed, keeping the pressure steady. This is especially important in systems where fluctuations could impact performance or safety. By managing pressure effectively, the pressure-regulating valve helps us achieve reliable and stable operation, which ties into the overall goal of keeping our systems safe, efficient, and well-maintained. Most turbine engine oil systems typically use a pressure-regulating type system, which is crucial for maintaining consistent oil pressure. This consistency ensures that all engine components receive the proper lubrication they need to operate smoothly and reliably. The key component here is the pressure-regulating valve, which automatically adjusts to keep the oil pressure within a safe and effective range. By doing so, it prevents pressure fluctuations that could lead to potential engine damage or inefficiency. This system is a vital part of the overall engine lubrication strategy, helping to enhance performance and extend the life of the engine. So, understanding how the pressure-regulating valve works gives us insight into how these engines stay reliable under various operating conditions. The oil pressure-regulating valve is an essential component in the oil system, and you'll find it on the pressure side of the pressure pump. Its main job is to help control the oil pressure within the system, ensuring it stays within safe and optimal limits. Think of it as a sort of pressure valve that prevents the system from becoming overpressurized. This is where the regulating valve system comes into play. It acts like a pressure governor, maintaining the system's pressure at a limited, predetermined level. By doing so, it protects the components from potential damage caused by excessive pressure. In essence, the pressure-regulating valve is crucial for maintaining the overall health and efficiency of the oil system. It ensures that the system operates smoothly and reliably, preventing pressure spikes that could lead to failures or wear over time. So, in the bigger picture, this valve helps us keep the entire system balanced and functioning properly, which is key to the reliability and safety of the machinery. So, what we're looking at here is actually more of a regulating valve than a relief valve. The key difference is that a regulating valve works to keep the system pressure within a certain range, rather than just opening only when the absolute maximum pressure is exceeded. It's designed to maintain a steady pressure level, ensuring the system operates smoothly and safely. This is especially important in applications where consistent pressure is critical for performance or safety. So, in essence, while relief valves are like safety nets that only act in emergencies, pressure-regulating valves are more like control devices that manage the pressure continuously during normal operation. This concept ties into our overall discussion on maintaining system integrity and safety. Let's take a closer look at how a pressure-regulating valve works. Essentially, this valve features a regulating valve that is held against a seat by a spring. The key idea here is that the spring applies a force that keeps the valve closed until a certain pressure is reached. When the pressure in the system exceeds this set point, it overcomes the spring force and pushes the valve open, allowing fluid to flow through. Once the pressure drops back down, the spring pushes the valve closed again, maintaining a consistent pressure level. This mechanism is crucial for controlling system pressure and ensuring safety and efficiency. Connecting this to our overall theme, it highlights how simple yet effective mechanical components like springs and seats can play a vital role in maintaining stable system operation. Now, let's talk about how adjusting the tension on the spring affects the pressure at which the valve opens. When we increase the spring tension, it requires a higher pressure to overcome that tension and open the valve. Essentially, you're setting a higher pressure threshold for the valve to activate. This adjustment not only controls the opening point, but also leads to an increase in the system pressure overall. So, by tuning the spring tension, you can precisely regulate the pressure within your system, ensuring it operates within safe and efficient parameters. This is a key concept because it highlights how pressure regulation can be customized to meet specific system needs, maintaining stability and performance throughout the process. Now, on this slide, we're looking at how a pressure-regulating valve works. Essentially, a screw presses down on a spring, and that action adjusts the tension on the valve. By changing this tension, we control the system's pressure. When you tighten the screw, the spring compresses more, which raises the pressure needed to open the valve. Conversely, loosening it reduces the pressure threshold. This setup allows us to maintain a consistent pressure in the system, regardless of fluctuations downstream. It's a simple yet effective way to ensure our system operates safely and efficiently. Remember, this component is crucial for stabilizing pressure and protecting other parts of the system from overload. So, understanding how the tension adjustment influences pressure helps us better manage and troubleshoot the entire setup. Let's take a closer look at the oil jet. This component is essential in the lubrication system, especially in high-performance engines. The oil jet is responsible for delivering a focused stream of oil directly onto critical engine parts, such as the pistons and cylinder walls. By doing so, it helps to efficiently cool and lubricate these areas, which are subject to intense heat and wear during operation. The most important concept here is the precision of oil delivery. Unlike a general oil spray, the oil jet targets specific zones, ensuring optimal cooling and reducing the risk of overheating or premature wear. This targeted lubrication is crucial for maintaining engine efficiency and longevity, especially under demanding conditions. Connecting this to the overall theme of engine performance, the oil jet exemplifies how specialized components work together to enhance durability and efficiency. Proper oil delivery not only prevents damage, but also improves overall engine responsiveness. So, understanding and optimizing these jets can make a significant difference in engine health and performance. Let's take a closer look at where the oil jets are typically located. You'll find them in pressure lines that are adjacent to or within bearing compartments and rotor shaft couplings. These areas are critical because they require precise lubrication to ensure smooth operation. Now, the oil from the nozzle isn't just released in any form, it's delivered as an atomized spray. This means the oil is broken into tiny droplets, which helps it spread more evenly over the necessary components. The use of an atomized spray ensures more effective cooling and lubrication, reducing wear and preventing overheating. Overall, understanding the placement and delivery method of these oil jets is essential for maintaining the reliability and efficiency of the system. Some engines use an air-oil spray that is produced by tapping high-pressure bleed air from the compressor to the oil nozzle outlet. This method is considered adequate for ball and roller bearings. Essentially, the high-pressure air helps atomize the oil, creating a fine spray that can be directed precisely where it's needed. This technique ensures proper lubrication without excessive oil consumption. It's a practical solution in many engine designs, especially when dealing with ball and roller bearings, which require reliable, consistent lubrication. Overall, this approach helps maintain the engine's efficiency and longevity by ensuring that critical components are properly lubricated. Today, I want to highlight that the solid oil spray method is generally considered better than the oil jet method. When we compare these two approaches, the solid oil spray offers some clear advantages, particularly in terms of consistency and control. It provides a more uniform coating, which is crucial for ensuring optimal lubrication and minimizing waste. On the other hand, the oil jet method involves spraying oil in a high-velocity jet, which can sometimes lead to uneven application and more overspray. While it might be suitable for certain situations, overall, the solid oil spray tends to deliver more reliable and efficient results. This choice aligns with our overall theme of improving process efficiency and ensuring better quality control. By adopting the solid oil spray method, we can achieve more precise lubrication, reduce oil consumption, and enhance equipment longevity. So, in our ongoing efforts to optimize operations, the solid oil spray stands out as the preferred method. Oil jets are a critical component in many engine systems, but they can be quite sensitive. One of the main challenges is that they are easily clogged. This is primarily because of the small orifice in their tips, which makes them vulnerable to blockages. If any foreign particles get into the oil, they can easily clog these tiny openings, disrupting the flow. That's why it's absolutely essential that the oil remains free of any foreign particles. Keeping the oil clean ensures that the jets function properly, maintaining optimal engine performance. Remember, the efficiency of the oil jets directly impacts the overall health of the engine, so proper maintenance and cleanliness are key. Last chance filters in oil jets are critical components, but they can become clogged over time. When that happens, it often leads to bearing failure, which can be quite serious. The tricky part is that nozzles are not easily accessible for cleaning, except during scheduled engine maintenance. So, if these filters become blocked between maintenance intervals, it can cause reduced oil flow and increase the risk of damage. That's why regular inspection and proper maintenance are essential to prevent these issues from escalating. Keeping these filters clean helps ensure the oil jets function properly, supporting the overall health and reliability of the engine. To prevent damage from clogged oil jets, it's really important to check the main oil filters frequently for contamination. When these filters get dirty or clogged, it can restrict oil flow, which might lead to engine issues or even damage. The oil jet, as you know, plays a crucial role in delivering oil precisely where it's needed. So, keeping an eye on the filters helps ensure that the oil jet functions properly. Regular inspection and maintenance are key to avoiding costly repairs down the line. Overall, this step is vital in maintaining the health and longevity of the engine, aligning perfectly with our theme of proactive maintenance and reliability. Let's take a moment to talk about the oil cooler. This component is essential for managing the engine's temperature and ensuring optimal performance. Essentially, the oil cooler functions like a radiator for the engine oil, helping to dissipate heat that builds up during operation. By keeping the oil at the right temperature, it prevents overheating and maintains proper lubrication, which is crucial for engine longevity. Highlighting its importance, a well-functioning oil cooler can significantly improve engine efficiency and reduce wear and tear over time. It ties into our overall theme of effective thermal management in engine systems, demonstrating how each component plays a vital role in keeping the engine running smoothly. In short, the oil cooler might seem like a small part, but it's a key player in safeguarding engine health and ensuring consistent performance under various operating conditions. Today, we're going to look at the two basic types of oil coolers that are commonly used in various systems. The first type is air-cooled, which, as the name suggests, relies on airflow to dissipate heat from the oil. These are often simpler and more straightforward, making them ideal for applications where space and weight are considerations. The second type is fuel-cooled, which uses the fuel itself as a cooling medium. This method is particularly efficient since it utilizes the fuel's heat absorption capacity, helping to keep the oil at optimal temperatures. Understanding these two types is fundamental because they each have their own advantages and are chosen based on the specific requirements of the system. Both play a crucial role in maintaining proper oil temperature, ensuring system reliability and performance. Air oil coolers play a crucial role in the lubricating systems of some turbine engines. Their main function is to reduce the temperature of the oil to a level that allows it to be safely recirculated through the system. By doing this, they help maintain optimal operating temperatures, preventing the oil from becoming too hot and losing its lubricating properties. This cooling process is essential for ensuring the engine runs smoothly and reliably. Overall, air oil coolers are a key component in managing engine temperature and protecting engine components from heat-related damage. Now, let's talk about the air-cooled oil cooler, which is typically installed at the forward end of the engine. This placement is strategic because it allows the cooler to effectively dissipate heat by utilizing the incoming airflow. The air-cooled oil cooler is quite similar in both construction and operation to the air-cooled cooler used on reciprocating engines. Essentially, it uses airflow to remove heat from the oil, helping to maintain proper engine temperature and prevent overheating. This design is straightforward but highly effective, especially in aviation where reliable cooling is critical. So, understanding how this cooler works and where it's positioned gives us a better grasp of the overall engine cooling system and its importance in ensuring optimal engine performance and longevity. An air oil cooler is typically included in a dry sump oil system to help manage the oil temperature. This component is essential because it ensures the oil remains at an optimal temperature for proper lubrication and engine performance. Now, this cooler can be either air-cooled or fuel-cooled, depending on the engine design and cooling requirements. In fact, many engines actually use both types of coolers to maximize efficiency and maintain consistent oil temperatures. The air-cooled oil cooler relies on airflow to dissipate heat, making it a simple and reliable solution. On the other hand, fuel-cooled oil coolers use the fuel itself to absorb heat from the oil, which can be very effective in certain engine setups. Overall, incorporating an air oil cooler, whether air-cooled, fuel-cooled, or both, is a key aspect of maintaining engine health and ensuring reliable operation in high-performance or demanding environments. First, air cooling of bearings by using compressor bleed air is not sufficient to cool the turbine bearing cavities because of the heat present in the area of the turbine bearings. As you can imagine, the temperature in this region is quite high due to the intense heat generated by the turbine operation. Simply relying on bleed air for cooling doesn't provide enough thermal protection. That's where the air oil cooler comes into play. It's essential for maintaining proper bearing temperatures and ensuring the reliability and safety of the turbine. This highlights the importance of effective cooling systems in managing heat and preventing bearing overheating, which is critical for overall engine performance. Now, moving on to the next point, it's important to understand that large turbofan engines typically require more bearings. This is mainly because these engines are bigger and handle more power, so they need additional support to keep everything running smoothly. However, having more bearings also means more heat is generated and transferred to the oil. As a result, managing this heat becomes crucial to maintaining engine performance and reliability. This is where oil coolers come into play. They are essentially the only means we have to dissipate the heat from the oil. Without effective cooling, the oil could overheat, which could lead to lubrication issues or even engine damage. So, in essence, The air oil cooler is a vital component in the engine's thermal management system, especially in large turbofan engines. It ensures that the oil stays within safe temperature limits, helping to keep the engine running efficiently and safely throughout its operation. Now let's take a closer look at the fuel-cooled oil cooler. Essentially, it functions as a fuel oil heat exchanger. What this means is that the fuel helps cool the hot oil, but at the same time, the oil heats the fuel, which is necessary for combustion. This reciprocal heating and cooling process is a key part of maintaining optimal engine temperature and efficiency. It's important to remember that the fuel that flows to the engine must pass through this heat exchanger first. This step ensures that the fuel is at the right temperature for combustion, preventing issues like fuel freezing or overheating. So, in summary, the fuel oil cooler plays a dual role. It cools the oil to prevent overheating and preheats the fuel to ensure smooth engine operation. This interconnected system is critical for engine performance and reliability, fitting into the bigger picture of efficient engine cooling and fuel management. On this slide, we see a thermostatic valve that plays a crucial role in controlling the oil flow within the system. What's interesting about this valve is that it can adjust the flow based on the system's cooling needs. If the oil doesn't require cooling, the valve allows the oil to bypass the cooler entirely, which helps maintain efficiency and prevents unnecessary cooling. Next, we have the fuel or oil heat exchanger, which consists of a series of joined tubes. Think of these tubes as pathways for the oil to transfer heat effectively. The exchanger has an inlet and an outlet port, allowing the oil to flow through these tubes, absorb heat from the surrounding environment or other system components, and then exit at a controlled temperature. Finally, the overall purpose of the fuel oil cooler is to ensure the oil remains at an optimal temperature for system performance and longevity. By managing the oil temperature through these components, the thermostatic valve and heat exchanger, we help maintain efficient operation and protect the engine or system from potential damage caused by overheating. This interconnected system is a key part of our overall thermal management strategy. Now, let's take a closer look at how the oil flows through this system. Oil enters the inlet port first, and from there, it moves around the fuel tubes. This movement is essential because it allows the oil to absorb heat effectively. After circulating around the tubes, the oil exits through the oil outlet port. This process is vital for maintaining proper temperature levels and ensuring the engine runs smoothly. By understanding this flow, we can see how the fuel oil cooler plays a crucial role in managing engine temperature and overall performance. Today, I want to introduce you to a fascinating figure known as de-oiler. This concept is quite central to understanding how energy and resources are managed within our broader system. Essentially, de-oiler represents the idea of rethinking traditional approaches to resource distribution and consumption. It's about finding more efficient, sustainable ways to allocate and utilize resources, which ties directly into the overall theme of innovation and sustainability in our industry. By examining de-oiler, we can gain insights into how to optimize processes, reduce waste, and move towards a more resilient future. This concept encourages us to challenge the status quo and explore smarter solutions, which is truly at the heart of what we're aiming to achieve in this presentation. Now, let's take a closer look at the de-oiler. The primary function here is to remove oil from the breather air, which is essential for maintaining proper system operation and preventing oil carryover. The breather air enters the de-oiler, where it encounters an impeller housed within the de-oiler housing. As the impeller spins, it creates centrifugal force that helps separate the oil from the air. This process is crucial because it ensures that only clean, oil-free air exits the breather system, helping to keep the entire setup efficient and clean. Remember, this step is key in managing oil vapors and maintaining the overall health of the system. Centrifugal force drives the oil towards the outer wall of the impeller, which is a key mechanism in the de-oiling process. As the impeller spins, this force causes the oil to move outward, effectively separating it from the gas. Once the oil reaches the outer wall, It can then drain away from the impeller and flow into a sump or an oil tank. This step is crucial because it helps in maintaining the efficiency of the separation process, ensuring that the gas is as oil-free as possible before moving on to the next stage. The deoiler's design leverages centrifugal force to improve separation, making it a vital component in the overall system. This process not only helps in oil recovery, but also keeps the equipment running smoothly by preventing oil buildup. Now, let's take a closer look at the magnetic chip detector. This device plays a crucial role in aircraft maintenance and safety. Essentially, it's designed to detect metal particles that may be circulating within the engine oil system. These particles can be a sign of wear or damage inside the engine components. The magnetic chip detector is usually installed in the oil sump or oil lines, where it can efficiently attract and hold metal debris. When metal particles are captured, the detector can be easily checked during inspections, giving us an early warning of potential issues before they develop into more serious problems. This proactive monitoring helps prevent engine failure and ensures safe operation. It's a simple yet highly effective tool, connecting directly to our overall theme of aircraft safety and maintenance. By catching metal debris early, we're able to perform targeted repairs, reduce downtime, and maintain the integrity of the engine. So, the magnetic chip detector might seem like a small component, but it has an outsized impact on keeping aircraft operating safely and efficiently. Magnetic chip detectors are an essential component of the oil system. They work by detecting and catching magnetic particles that are present in the oil. These particles often come from wear and tear inside the engine or machinery. By catching these particles early, magnetic chip detectors help us monitor the health of the engine and prevent potential failures. They are particularly useful because they provide a simple, reliable way to identify metal debris before it causes more serious damage. Integrating magnetic chip detectors into the oil system is a key step in proactive maintenance and ensuring the overall reliability of the engine. All right, as we wrap up, let's take a quick look at what's coming next. The next lesson will focus on the scavenge system. This is an important topic because it ties into how we efficiently manage resources and optimize processes. We'll explore how the scavenge system works, its key components, and why it's vital for maintaining system health and performance. Understanding this will help you see the bigger picture of system maintenance and sustainability. So, stay tuned for that, and I look forward to diving into it with you next time.